Hello everyone, I'm Jesús Yepes from Universidad de Murcia, and I will go on to talk about new properties of the Vis functional, which is, as we have planned, the second part of the talk by Maria Hernández-Cifre, also from Universidad de Murcia. And this is about a joint work of us with David Alonso Gutiérrez from the Universidad de Zaragoza in Spain. First of all, for sure, I would like to thank the organizer of this beautiful trimester with many very nice activities that we have enjoyed very much. And it is our pleasure to take part of some of them. So, although I'm assuming that all of you have watched previously the video by Maria, let me very briefly recall you some basic from her talk. The Vis functional is defined as the sum of all the ith intrinsic volume of the complex body K. This ith intrinsic volume will be denoted by Vi, as she has mentioned before. This functional has many beautiful properties, as she has already mentioned. But among all of them, I will focus on some internal representation of it that were given by Hadwiger mainly around 50 years ago. And among all of them, I will focus on especially in the following one. The Vis functional of a complex body K can be obtained as the integral of the negative exponential function of pi times the Euclidean distance between x and the complex body K squared. Since this distance is a complex function, then the function that appears here under the integral sign is a log concave function. But moreover, as Maria has mentioned before, this is not only a log concave function, but also the assumed product of two other log concave functions: the characteristic function of the complex body K and the negative exponential function of pi times the Euclidean norm squared. And these two facts will be the key points of our approach. So what we did here is exploiting all the machinery that one can find in the literature for log concave function in order to study whether of the well-known inequalities for the volume are still true for this functional. Maria has shown you before some Reyes-Seffer type inequalities, the one result of the in the spirit of what happens for the volume when it is in joint position, and some other properties. And here I will mainly focus on some Brun-Minkowski type inequalities. So before presenting our result, let me recall you very briefly the well-known Brun-Minkowski inequality. This result says the following in terms of the ith intrinsic volume. It can be summarized by saying that the ith intrinsic volume is 1 over I concave when dealing with complex bodies, which means nothing but that the ith intrinsic volume of every complex combination to the power 1 over I is bigger than the complex combination of the intrinsic volume, of these bodies, to the same power. So in particular, all of them, all the intrinsic volume, are 1 over n concave as the volume. This, together with the following result for orthogonal boxes, made us to wonder ourselves about the possibility that this functional also satisfies a Brun-Minkowski inequality in its classical form, I mean with exponent 1 over n. What happens here for orthogonal boxes is exactly that. This function of the complex combination to the power 1 over the dimension is bigger than the complex combination of this functional of these guys to this power. This can be easily obtained by taking into account one of the properties that Maria has shown you before, this property that says, roughly speaking, that the Vis functional behaves well in terms of Cartesian product. So using that, one can obtain this. And then, since orthogonal boxes approximate very well, union of them for sure, approximate well compact set, and also taking into account that all the intrinsic volume are 1 over a concave and the Vis function is nothing but the sum of all of them, it is natural to wonder, as I was telling to you before, that this functional should be also 1 over n concave. However, unfortunately, this is not the case. It is very easy somehow to find different pair of complex bodies for which the inequality holds with a reverse sign. However, nevertheless, this result, this spectrum inequality is not very far away from being true in the following sense. Just by adding the following constant, the constant 1 over n factorial to the power 1 over n, which is of the size of E over n, then you get such an inequality. I mean, the base functional of the convex combination of two arbitrary convex bodies to the power 1 over the dimension n is bigger than the convex combination of this functional to the same power times this constant that I mentioned to you before. So for sure, this is not a real concavity property for such a functional, but if one wishes such a concavity result, what one gets is that what holds true is a log concavity property. I mean, what is true is the multiplicative version of the Bloom-Minkowski inequality for this functional. I mean, the base function of the convex combination is greater than the zero mean, I mean the geometric mean of the base function of them. We obtain this as an application of the above mentioned integral representation for the base functional jointly with the precovalent inequality. But moreover, somehow what we checked is that this is the best concavity that one can expect for such a functional in the following sense. By making some numerical computation, we found some counterexample for any expected 1 over p for p large enough concavity. I mean, if one expects 1 over p concavity for arbitrary dimension, one fails. I mean, at the end, you find a dimension large enough for which the opposite inequality holds for certain pair of convex bodies. But nevertheless, in some particular dimension, you can still get further dimension, further concavity properties, sorry. And this is the case of the plane. I mean, in the plane, what we got is 1 over 2 plus 1 concavity. This is what the following result says. For two planar convex bodies, the base functional of the convex combination to the power 1 over 3 is bigger than the convex combination of the base function of them to the same power. The key tool here was the following. As I mentioned before, we were exploiting the integral representation in terms of the above log concave functional depending on the distance between the point and the body for this function, this formula. But moreover, what we did here, our approach was in terms of study, a more general family of functional. I mean, not only the base functional, but those functional that are of above type, but by considering other log concave function, not only this e to the power minus pi times t squared function applied to the distance, but other log concave function. By means of that, by means of studying this more general functional, one still have the chance to get sometimes the base functional when working with other function. And if those functions, many times you only get that such a formula for the base functional holds true for a certain dimension, as in this case. For instance, in dimension 2, what we found is a precise integral formula involving another function. And since this function satisfies further properties, let's say, than this exponential, this negative exponential, we were able to get a further concavity property for the base function. So this is what we got in terms of Bloom-Minkowski type inequalities. And what about reverse forms? Well, for sure, let me first of all to point out that even for the volume, one cannot expect to get a reverse Bloom-Minkowski inequality, just in the sense of bounding from above the volume of the Minkowski sum in terms of the sum of the volume of them with certain powers. Because even when dealing with convex bodies of volume 1, one can always find pairs of convex bodies with volume 1 such that the Minkowski sum has arbitrarily large volume. And then one cannot find an upper bound depending only on the volume and with a constant. But however, by introducing some transformation, one has something like the following result. This engaging result by Millman from the 1986, which says that whenever you consider two convex centrally symmetric bodies with interior point, then there exists always a volume and orientation preserving linear transformation and a positive absolute constant, such that the volume of the Minkowski sum of K and this transformation acting on L to the power 1 over the dimension is smaller than such a constant times the sum of their volume to the power 1 over n. So in this sense, and although as we have seen before, the general Minkowski inequality, I mean, in its form with exponent 1 over n, it is not true, but what holds true is the multiplicative version of it. However, when dealing with the reverse form, what happens is that the Wiss function actually satisfies the same inequality. I mean, if you consider two convex body K and L, then there exists always a volume and orientation preserving linear transformation and a positive absolute constant C, such that the Wiss function of the sum of K and the transformation by means of T of L to the power 1 over the dimension is smaller than such a constant time the sum of the Wiss functional to the same power. So essentially, it's exactly the same just by replacing volume by the Wiss function. And with this, I think I will conclude my talk. So thank you very much for your attention.